Okay, shall we start?
Yeah.
Thanks, Daisy.
Good evening, also good morning and good afternoon, everyone. Welcome to our Ecomat webinar series. And today's topic is perovskites for highly efficient solar cells. My name is Daisy Diao. I'm the journal published manager of Ecomat from Wiley, China. First of all, please allow me to give a quick introduction about our journal. Ecomat is a top-tier journal published by Wiley in collaboration with the Hong Kong Polytechnic University. It is a gold OA journal aiming to publish on a wide variety of topics from different disciplines that share a focus on cutting-edge materials for green energy and the environment. The scope of Ecomat is intentionally broad, including the energy harvesting, storage and conversion, energy system as networks, fuel cells, piezo and triboelectrics, water and air pollution control, etc. The articles can be immediately opened once published. We also have a rapid average publication speed, so welcome your submissions. Ecomat is expected to make a mark in material science and its adjacent fields with ambitions of high academic impact, just like energy materials and advanced materials. We have already published 10 issues online so far, and our article publication charges are still waived until next year's end. The journal has already been indexed by Web of Science ESCI, DOAJ. Now it is also in the evaluation process of SCIE. Here, I would also like to introduce our dedicated editorial team briefly. We have Professor Zijian Zheng from Hong Kong Poly U as our editor-in-chief, and 4 associate editors who are Songbin Yuan from Northwestern University, Sam In-suk from UNISD South Korea. He is also our moderator today, and Huijun Zhao from Griffith University, and Xiang Zhang from Tsinghua University. We also have our managing editor, Dr. Lo, and he Hong Kong. Last but not least, on behalf of Ecomat team and Wiley, I would like to thank you all for your continuous care and support to this journal. We look forward to your submission. Currently, we accept the research articles, the reviews, and research highlights. Also, we welcome you to follow our social media accounts, and please scan the codes, and you will find us on WeChat, LinkedIn, Facebook, and Twitter. Now I'd like to hand over to Professor Suk to start today's webinar officially. And please do not hesitate to raise your questions in this webinar. Let's start. Thank you.
Professor Sok, you have to open your microphone.
Sorry. Yeah. So I say again, okay. So thanks for the great introduction to the Ecomat. So I'm very proud to invite the speak host of today's webinar. So as I already introduced, I'm Sanil Sok, who is the professor at Ulsan National Institute of Science and Technology, and the associate editor of the Ecomat. So today's agenda consists of the 30-minute presentation from the 2 invited speakers, followed by the 30-minute roundtable discussions. So as we know very well, in the last decade, research on the metal hard perovskite has made tremendous progress. The certified efficiency of the solar cell based on the hard perovskite material has already reached close to 26 and can now compete in this respect with the silicon-based solar cell. So, however, its efficiency still apart from the theoretical value and neither further improvements. So even though there are so many factors affecting the power conversion efficiency, it's a necessity to improve the key property of the perovskite material itself as right absorbing materials. So one of them is to fabricate the single crystal like the thin film with the few defect, which is very high quality of thin layer. And other is to expand the right absorption spectrum, solar spectrum, by the narrowing the band gap of the halide ferrous materials. Of course, the multi-junction tandem solar cells can be fabricated by stacking the perovskite and the silicon and the CIGS, so on. Today, we have the webinar by inviting the two leading researchers in this field. Okay, now time to start our have the invited speaker. The first speaker is the Professor Osman Bakr. So let me briefly introduce him. He received his bachelor degree in the material science from the MIT in 2003, and his master and PhD degree in applied physics from Harvard University in 2009. He is currently the professor of material science engineering at KAUST. The full name of KAUST is the King Abdullah University of Science Technology. His research group focused on the study of the hybrid organic nanoparticle and materials for application in electronic and catalyst. So I know his paper, low trap state density and long carrier diffusion in organolead 3 halide perovskite single crystalline, published in the Science in 2015, has more than 3,000 citations. Title: the Professor Osman Bakr present today is the metal halide perovskite single crystalline solar cell, from high efficiency to fundamental insight. Okay, please welcome him.
Thank you.
Professor Bakr.
Thank you, Professor Suk. Can you see my screen?
Yes.
Wonderful. All right. Thank you very much, Professor Suk, and thank you. I'd like to thank the organizers, Ecomat, for inviting me to be part of a distinguished panel of speakers. It's a great honor to be introduced by one of the heroes of the field, Professor Suk. Of course, he's and also one of the pioneers and really one of the distinguished researchers, also being part of this panel, Professor Helen Tan. So I want to tell you a bit today about some of the work we're doing in my lab, and that's mostly we work on perovskite single crystals, but we also work on nanocrystals and other related areas of perovskites. Before I begin, I'd like to actually thank my students who are and my postdocs who actually did this work. I've been lucky enough to have outstanding group members who've been publishing outstanding papers over the years. And I've also been fortunate enough to be working with great collaborators. A lot of our work is done in collaboration with other groups, including Professor Omar Mohammed, who does a lot of the spectroscopy in our studies, and Professor Ted Sargent as well. Our funding comes from the King Abdullah University of Science and Technology, but we also have a few industrial companies that like technology, including Saudi Aramco and Sabi. So our group works on design and synthesis of perovskite materials, but we also look at different applications. I know this seminar is about solar cells, but actually perovskites are in fact very versatile semiconductors, and they cover almost any kinds of optoelectronics. And so they can be used in LEDs, photodetectors, phosphors, and even in, as we've shown recently, in high energy radiation detection. But today I'll be telling you about our work on solar cells. And for those of you who are not familiar with perovskites are these ionic compounds that have this ABX3 formula, where B is in an octahedra of X, and A is in a cavity inside, surrounded by BX6 octahedras. And many elements can form this perovskite structure as long as they obey this tolerance factor. And as long as the tolerance factor is close to 1, then a lot of materials do form this compound structure. Researchers are interested in perovskite structure because of its tunable band gaps, high absorption coefficients, and defect tolerance, and also long carrier diffusions. So that means there's a lot of applications that we can consider for this outstanding semiconductor. But also, there's a lot of versatility in the structures that it forms. You could form the classical perovskite structure, but if you start adding large A-side cations, you could start breaking up the perovskite network. You could form 2-dimensional perovskites, 0-dimensional perovskites, 1-dimensional perovskites, and even if you use surfactants, you could start thinking about you could start making colloidal nanocrystals. If you are interested in this topic, I would urge you to look at perspective we wrote about different dimensionalities that perovskites can adopt. People start getting interested in perovskites because, of course, the efficiencies have been growing really quite rapidly. Professor Suk, I think, several times broke the records in perovskites, but every year we get a different record, and this year and the last year we've now surpassed silicon technology, and just to add, perovskites are solution processed at low temperature, and they can be compatible with low cost manufacturing methods. So that's a very exciting thing, that you have a technology that's very efficient at the same time compatible with large scale low cost manufacturing. Now most of the community were focused on perovskite polycrystalline solar cells and polycrystalline materials, and so we wanted to look at single crystals because we wanted to see the material without being obstructed by or obscured by grain boundaries. And so with our first try at this is the 2015 paper we did with that Professor Suk alluded to. We started crystallizing perovskites in a very simple way, and most people use these kind of crystallization methods in chemistry and biology, but actually no one applied it to perovskites at the time, or applied it to grow large perovskite crystals. And so we dissolved perovskite crystals in a good solvent and stored them in an anti-solvent, and over a matter of a few days to a week, we started getting the diffusion of the anti-solvent, and we started getting large crystals forming. And we wanted to look at the carrier diffusion, how far photoexcited carriers would travel, and we wanted to estimate that. So we could only do that at that time in an indirect way. And so we measured the mobility of the material, we measured the lifetime, and we used the Einstein relationship to extract diffusion length. And at that time, we realized that the diffusion length was about at least more than 10 microns. And that was a real surprise, because at the time when people who worked with polycrystalline solar cells estimated that diffusion length was a few hundred nanometers. So this created a much bigger expectation in the field, an expectation that this material can do a lot more than what people think. So the second step for us was, what can we do with single crystals? If it takes a month to grow them, what's the point? Or it takes a week to grow them, what's the point? So I'm going to show you a method that we discovered how to grow them in a few hours, and sometimes even a few minutes. So the discovery came when my postdoc Maksud noticed that when we dissolve or saturate a solution of perovskites in a coordinating solvent, and you raise the temperature, you start noticing crystals forming, precipitation happening. So this was very strange because normally when you raise the temperature, more material would dissolve. But in fact, when we raise the temperature, material precipitated. When we cooled the temperature, the material dissolved. And we kept doing this over and over, and we found this is a very reproducible phenomena, and it's called retrograde solubility. So it's called inverse crystallization. And we measured the solubility of different perovskites in different coordinating solvents, and we found that indeed the solubility drops as you raise the temperature. Sometimes it's non-monotonic. And just to give you an idea, if you do this process, because when you raise the temperature, you're suddenly putting the solution under conditions of supersaturation. And if you do this carefully and you nucleate with just one crystal, you can, in a matter of minutes and hours, grow a crystal that normally takes a week to grow. Okay? So this was an exciting discovery for us. And at the time, we also noticed that we could use this method to grow crystals into the shape of the vessel that we wished. We weren't sure what to do with it at the time, but I'll show you later why is that important. We could keep growing the crystal over and over again. And so, this process can be used to grow crystals large and small. And we showed that virtually, so many perovskite materials fall under this inverse temperature crystallization approach. And it's applicable to a lot of different perovskites as long as you use the right coordinating solvent. So the second question that came up to us was, we have single crystals, they're nice for fundamental studies, but can we use them for devices? And to use them for devices, you have to either make them thin, you have to make them thin enough for device applications, and that requires either normally you find a way of slicing them or mechanically polishing them, or ideally you find a way of actually growing them thin enough to begin with. And our first method to grow them, we used we found that if you do the growth of the perovskite crystals and you introduce a sonication pulse before supersaturation, you actually create a cavitation pulse that spreads the crystal on the substrate. And here's a crystal we grew that's a few millimeters in lateral dimension, but it's only a few hundred nanometers in thickness. And at that time, we fabricated the first thin film single crystal perovskite, monocrystalline perovskite solar cell. And at the time, it wasn't very efficient because actually we were only able to grow the crystal from a wide gap material. But it was really instructive for us because what we found is that you could still get a decent efficiency without using any whole transport material, and the efficiency was quite stable, relatively stable, and in comparison to thin film polycrystalline solar cells. So this got us into the idea of growing single crystal perovskites. And at the time we were, the field was still trying to understand whether there's any use for these materials. And Professor Jinsung Huang's group from North Carolina State, they figured out that they could use inverse temperature crystallization methods, the same method we discovered. They could instead, by confining the growth in between two substrates that contained, on each side had either a whole transport layer, they could then grow the single crystal and into it's still a very thick, relatively thick crystal, but then they could also create a relatively efficient device out of it. And that was interesting to us because that was a relatively high jump in device performance relative to other single crystal reports. And so what we noticed is, if we grew the crystals under more controlled conditions, if we were very careful about the interface and how we use fresh solutions and everything, we realized that actually we could grow single crystal solar cells that are 20 microns thick, but have efficiencies that are more than 21%. So that was a big surprise because normally people thought that you needed very thin polycrystalline cells, very thin perovskite layers, hundreds of nanometers, a few hundred nanometers, you couldn't go beyond that. Otherwise, you would lose a lot of efficiency. But here we showed that we have an active layer that's more than 20 microns thick, and you still have a very efficient solar cell, and the fill factor is quite high. So, and we demonstrated that you could, the nice thing about single crystals is that you could actually capture more of the because it absorbs more light closer. It has an effectively lower band gap than polycrystalline films at the band edge. So the second step for us was, can we improve this process further? Because we realized that we were growing the crystals were being grown at relatively high temperatures, 100 and something degrees, 120 degrees. So we started looking at different solvents, and can we reduce the crystallization temperature? And what we found is that if we mixed GBL with with propylene carbonate, we could lower the crystallization temperature. We would, in fact, we found that we could reduce the amount of lead iodide that forms on the surface of the crystal, and thereby improve the interface, improve the VOC of the crystal, and we can improve the efficiency almost to 22%. Step was for us to, can we play around with the band gap? Can we shift the band gap with the single crystals? And of course, people have done a lot of work on polycrystalline films, but growing single crystal cation is not that trivial. And with a lot of effort, one of our brilliant students, Abdullah Saloom, found that he could grow mixtures of formamidinium, methylammonium, lead iodide crystals. And what was really surprising is that, in fact, he was able to shift. He showed that formamidinium 60%, methylammonium 40% had a narrower band gap than polycrystalline formamidinium lead iodide. So we ended up shifting the EQ spectrum even a few tens of nanometers beyond what people are familiar with just polycrystalline lead iodide, and we were closer to the sort of band gap that we would like to get from ideal materials like gallium arsenide. And because of that, we were able to improve the efficiency even further, push it to 22.8%, and that was a big step for our field. And the surprising thing is to see that mixtures of formamidinium and methylammonium would give us a significant shift beyond what we normally had expected from just pure formamidinium. And we have very large short circuit current densities. So then we wanted to go back to, what can we do beyond making solar cells? Can we answer the question of what is the typical diffusion length in perovskites? Because we had a lot of, there was a lot of questions and controversy. What is the real diffusion length? And what is the diffusion length in the device when it operates? And many people said single crystals are not that much better than polycrystalline films. So what we wanted to see is what is the diffusion length in this material. And so what we did was we started growing single crystal devices of different thicknesses, starting from 20 microns, all the way to 300 microns. And we wanted to see what happens to the different different characteristics of the device. So what happens to the short circuit current? What happens to the VOC? What happens to the fill factor? And in fact, what surprised us is, actually you could make a device that's relatively efficient, even though it's a few hundred microns thick. And so you'll see that the power conversion efficiency only starts really dropping quite substantially when you start going above 200 microns. And so then what you could do is you could look at these current trends. Working with our collaborators from the University of Swansea, they developed an analytical model to estimate the electron diffusion length based on the trends we see, the thickness versus thickness, the trends we see in the short circuit current densities. And what we found is that actually, if you fit this model to our solar cells and the short circuit current density as a function of thickness, we find that actually the diffusion length of electrons in the device actually exceed 500 microns. So that's really surprising to us, and it shows that actually, this material is quite remarkable, and there's a lot for us to understand, and there's a lot for us to do in order to really apply this material to different applications. And now I want to just put a challenge to to our colleagues and many of the young researchers to say that there's a lot of work on polycrystalline cells, and maybe there's a few thousand papers every year, but there's only maybe a few tens of papers so far that have been published on single crystal cells. And despite that, we're growing very close to polycrystalline cells. So I think it's only a matter of time if people invest in this single crystal technology, we'll be able to catch up with polycrystalline technology. The biggest challenge for us, of course, although we have very interesting, very compelling optical properties and optoelectronic properties, how can we grow single crystals, on a very large scale so that we could make them for large area devices? So that's something we haven't yet figured out, but we're working on, and I hope people in the field can solve that issue. Before I conclude, I'm just going to tell you also a bit about what we did in nanocrystals, and how it inspired us to do some things to make some contributions to polycrystalline perovskite solar cells. So perovskite nanocrystals, or sometimes quantum dots, were essentially first introduced by Kovalenko's group, and they showed the first kind of real perovskite, and they showed that these materials can be tuned. Their color can be tuned by changing the highlight composition, and you had a monodispersed solution of perovskite nanocrystals, but they were capped with oleic acid and oleolamine, and that actually turned out that it caused a defect on the surface because oleic acid and oleolamine reacted, caused an acid-base reaction that degraded the surface and eventually caused trap states and degraded the photoluminescence of nanocrystals. And so what we try to look at is, can we apply ligand exchange methods to replace the native ligands like acid and something else? So we started with alkyl ammonium ligands, and we noticed that when we did replace oleic acid and oleolamine with alkyl ammonium ligands, we noticed that the stability of the nanocrystals jumped quite a bit, became a lot more stable, and also if we made devices from these materials, we had a significant jump in electroluminescence. At the time, these numbers sound modest, but in 2016, these were actually quite high numbers for nanocrystals, LEDs based on perovskite nanocrystals. In fact, at the time, that was a record for 1.9% EQE was a record for blue LED perovskite LEDs. Of course, now the field jumped since then, is now much more advanced, and people figured out how to stabilize perovskite materials, perovskite nanocrystals for LEDs as well. But we also were inspired by these ideas that we developed for using ligand exchange and using alkyl ammonium ligands. That we started looking at, can we apply this to perovskite nanocrystals, perovskite thin films, and we applied them to perovskite thin films. We looked at short and long chain alkyl ammonium ligands, and we found is that we could use, when you used short chain, trace amounts of short chain and long chain alkyl ammonium ligands, you could actually control the nucleation of the perovskite film and the orientation of the perovskite, and you could also stabilize the surface and in fact improve the stability of the material quite a bit. And we were able to obtain, at the time, was a record for PIN type inverted solar cells. And it just showed us that there's a lot of concepts that we could learn from nanocrystals that could be useful for solar cells. And in fact, one idea we had was we showed that we could use nanocrystals or perovskite nanocrystals in the processing of perovskite solar cells. Nanocrystals can have specific compositions, specific amounts of chlorine, specific amounts of different dopants. And because they're very dispersible and soluble in the organic solvents that are used to process perovskite solar cells, you could use them, in fact, to dope perovskite solar cells. And this is one idea we used, how to use perovskite nanocrystals to dope perovskite solar cells. And we showed that you could, in fact, improve the stability of perovskite films, and reduce the amount of defect states just by using perovskite nanocrystals as dopants and as carriers for different dopants. So I just, before I conclude, and I want to tell you that I showed you simple crystallization methods to make high quality semiconductors that lead to really impressive solar cells. Single crystal solar cells can really be a very important technology that complements polycrystalline films and the efforts that are being done, and can be used as a model system to really understand what's happening to the charge carriers in perovskites. And I'd like to thank everyone, and I hope you've gained by listening to me. And I just want to say also that our lab is always welcoming exceptional students and postdocs. And thank you very much. Professor Suk, maybe you want to unmute yourself?
Okay, sorry. So thank you for your nice talk. So after having the presentation from Professor Tan, we will schedule to have the round table discussion. Please join the schedule. Let me move to the next speak. The next speak is Professor Helen Tan. He's currently the full professor in the College of Engineering and Applied Science at Nanjing University in China. He received the bachelor degree and the master's degree from the Central South University and Institute of Semiconductor, the Chinese Academy of Science in 2008 and 2011, respectively. And then he obtained the PhD degree in 2015 from the Delft University of the Technology in Netherlands. During his PhD, he worked on the multi-junction thin-film silicon solar cell and the right measurement for silicon photovoltaics. After that, he studied the perovskite solar cell and Professor Ted Sargent's group at the University of Toronto as a postdoctoral researcher for 3 years from the 2015. Then he joined Nanjing University in 2018 after receiving the National 1000 Young Talent Award in China. His current research focuses on the developing the high efficiency and cost-effective photovoltaic devices, including perovskite solar cell, silicon solar cell, and perovskite-based tandem solar cell. Today, he will present about the efficient and stable monolithic or perovskite tandem solar cell. Okay, please, Professor Tan. Okay.
So thank you, Professor Sok, for your warm introduction and your invitation so that I have the opportunity to give a talk on our group activity on making efficient and stable all perovskite tandem solar cells. So in the previous talk, Professor Osman Bakr has detailed discussed the fundamental properties of perovskite materials and especially making very efficient solar cells using single crystalline perovskite crystals. And in my talk, I will expand the application of perovskite material to make even more efficient devices by combining the wide bandgap perovskite and the narrow bandgap perovskite to make tandem devices. So my talk will be divided into 3 parts. I will introduce the structure and the progress of all perovskite tandem devices, and then I will discuss our group works in the past 3 years work focused on the device engineering strategies toward making efficient tandem devices, and especially in the following 5 sections. And at the end, I will briefly discuss the stability of all perovskite tandem devices, because stability is a crucial factor that will determine the commercialization of the perovskite solar cells. Professor Osman Bakr has introduced the excellent properties of perovskite materials, and in addition to his introduction, I think perovskite material is very promising for low-cost and high-efficiency tandem devices, especially because we can easily tune the band gaps of these perovskite halide perovskite materials by changing the composition, especially like the halide composition at the X sides and also the metal cations at the B sides. For example, if we mixing the lead and tin at the B side, we can even lower down the band gaps of the perovskite down to 1.2 eV. So currently in the PV community, there are many 3 structures for perovskite tandem devices that has very high promise for very high efficiency. And the perovskite with wider band gap is usually work as the top cell. And depending on the narrow band gap material used, we can have crystalline silicon, or we can also have narrow band gap copper indium gallium selenide. And we can also reduce the band gap of the perovskite materials itself, so that we can also make the tandem devices all only using perovskite materials. And among these 3 tandem device structures, actually, they can all have practical efficiency, like practical efficiency limit above 33%. And all that tandem devices has the highest SQ limit efficiency among those 3 structures. And in the past 4 years, and mainly due to the very fast efficiency progress of the narrow bandgap perovskite solar cells, and also the progress of the all perovskite tandem devices is also getting very fast. And currently, the highest certified efficiency is recently obtained by our group is 26.4%. And this efficiency is already higher than the best performing single junction perovskite solar cells as obtained by the group of Professor Salk. But still, we know that the theoretical efficiency of the tandem devices is about 40%, and we still have much room to improve the efficiency for these tandem devices. And next, I will introduce our group activities, our strategies to making more efficient tandem. And when I first built my own group to work on this tandem project, and we have to first make efficient narrow bandgap perovskite solar cells by using the mixed lead tin cations. But we found there's several challenges for this material. The first is the easy oxidation of the tin 2+ ions, and this will result in a very high trap density and short diffusion length in the resulted perovskite films. And also due to the introduction of the tin ions in this precursor solution, usually the perovskite film crystallization becomes very fast and inhomogeneous. And this is usually led to poor morphology or non-uniform electronic qualities in the films. So before the year of 2019, the performance of the tandem devices actually is largely limited by the mixed lead tin-based narrow bandgap perovskite solar cells and materials. So our first strategy is starting from the year of 2017, actually, when I was a postdoc in Ted Sargent's group in Toronto. So I worked with another students that we get an idea. Maybe we can cap the grains of the mixed lead tin perovskite grains with an argentine two-dimensional perovskite materials. So what we do is different from the traditionally used surface passivation just by spin coating, for example, the long chain ligands PAI on top of the perovskite film. So what we did is different. So we added this long chain ammonia ligands in the anti-solvent so that we can get 2D perovskite materials not only on top of the film surface, and we think that this 2D layer can also form on the at the gram boundaries, so that it will have better passivation. So this is we approved our ideas actually through the PL decay measurement. So we found that using this, we call it is in-film passivation. So we can get a longer carrier diffusion length, not only on the top surface, but also at the bottom surfaces. And another benefit of this capping layer is that we can much reduce the surface oxidation of the tin 2+ ions. And in this way, we can much improve the performance and also the stability of this narrow bandgap perovskite solar cells. So by this way, so when we use a absorber layer with 400 nanometers, so we can get a higher performance. But we can see from the EQE spectra that due to the very thin absorber layer, so the JSC value is only around 27 milliamp per centimeter square. And later we use the carbon 60 evaporated as the electron transport layer, so we can use a thicker absorber layer, but still limited by the diffusion length of this material. So we can only use thickness up to 650 nanometers. So, and in this way, we can further increase the JSC value of the devices, and the efficiency becomes 19%. But from the previous EVD layer capping on the surface, we still found a quite high ratios of tin oxides in the perovskite materials. So we think about maybe this oxidation already happens in the precursor solution. And if this happens, and it will incorporated in this perovskite film, and it will generate the p-type doping and also the tin vacancies in the materials. So if we can prevent the tin oxidation in the precursor ink, so we have the way to much reduce the tin vacancies and also reduce the p-type self-doping. So what we do is we add the tin powders in the precursor solution, because the tin powders can reduce the tin 4+ states back to the 2+ states. That is what we need for perovskite materials. The benefits of this strategy is that we can much increase the charge carrier lifetime, and also we can slightly increase the mobility of the material. So as the final results, so we can increase the diffusion length of the materials from below 1 micrometers to above 3 micrometers. And this diffusion length is already very comparable to the full lead-based perovskite materials that can give efficiency higher than 24% nowadays. So means that by using this tin-reduced precursor strategies, we can increase the diffusion length of the perovskite up to 3 micrometers. So the benefits of this increased diffusion length that we can use even thicker absorber layer up to almost 900 nanometers, then we get the best efficiency is around 21%. And from the EQE spectra, we can see that due to the use of thicker absorber layers, we can get higher light absorption close to the band gap, and the JSC from integrated from the EQE is almost 32 milliamp per centimeter square. And this is actually a big advance, especially to get a high photo current density. That is what we need for tandem devices. So the next step that is we want to combine this improved nylobanding perovskite with wide banding perovskite to make tandem devices. And actually for solution processed all perovskite tandem devices, so one challenge is that how to protect the first perovskite layer during the fabrication of the second perovskite layer. So we need a solvent barrier layer. And this barrier layer is also used as a tunnel recombination junction actually in tandem devices. So what other researchers did before in the community is that they have to use a very thick ITO layer in the middle of the two subcells to prevent the solvent diffusion. But this very thick ITO layer actually is generate very high optical losses, and also it generates a very high leakage current in the tandem devices that will limit the performance. So what we do is we use the atomic layer deposition approach to deposit a very compact tin oxide film, and that is around 20 nanometers thickness. Use a very thick absorber layer for this layer so that we can get a higher matched current density. But this is not enough. So we found that if we directly use depositing P dot on top of the tin oxide layer, so we found that the fear factor of the tandem devices is quite low. So we suspect that this may be due to the not efficient charge recombination inside between the two subcells. So to increase the charge carrier recombination, actually, so we deposit another very thin layer of gold by evaporation on top of the tin oxide. So this strategy will increase the fear factor of the tandem devices considerably. And later, and then by using this, so we tune the thickness of the two subcells to get current matched condition, and then we can get a tandem device efficiency close to at that time. And we also make even larger area devices by increasing active area up to 1 centimeter square. So we can still get efficiency higher than 22%. And at that time, it's quite promising. Like, it seems that we can even make a larger area tandem devices. But still, like, we can see that if we increase the small area lab devices up to 1 centimeter area devices, we still lost 2.5% absolutely in efficiency. And this is also challenging not only for tandem devices, I think it is also for the single junction perovskite devices. So for tandem devices, to make a larger area devices, the challenge is that the faster crystallization of this mixed lead tin perovskite materials that usually resulted in non-uniform film. And also it will generate high trap densities on the film surfaces and the grain boundaries. So next, we carried out another work that maybe we can add some additive in the precursor solution so that we can modulate the crystallization process, and also we can passivate the defects on the surface and the grain boundaries. So what we choose is a kind of sweet ionic molecule. We call it is the formamidine sulfonic acid. So we add a very tiny amount of this additive in the solution. So these molecules, because it can coordinate, like this is a sulfonic group and also the formamidine group, they can coordinate with the metal ions, so that it may enable a delayed and even a more uniform crystallization. And also the sweet ionic functional groups, they can passivate the positive and also the negative charged defects on the grain surfaces. And also the sulfonic group, it is a strong reducing agent. It has the ability to suppress the oxidation of tin on the grain surfaces. So from the PL mapping of the samples, we can see that after introducing the additive, due to the surface passivation, we can see the emission is brighter, and also the charge carrier lifetime is increased. And also we can see from the emission, we can see that it becomes more uniform. And that due to the three benefits, so we can see that even for 1 centimeter area devices, the efficiency is increased from 16% to almost 19% efficiency. And also due to the grain surface passivation, and we can see that even for smaller area devices, the VOC, the open circuit voltage, is increased considerably, so that we can get a higher average efficiency. So the best efficiency for single junction devices, we can increase from the previous 21%, we can get almost 22%. And we send one devices to Newport for certification, and we know that certification of the team-based perovskite solar cells is quite challenging, but we will still manage to do that, and we get a stabilized efficiency of 20.7%. So the next step, we try to fabricate larger area tandem devices. Another challenge is that for the deposition of uniform vital band gap perovskite on the traditionally used polymer-based whole transport layer, because the surface weighting is not good, and because the contact angle is very large. And then we next think about maybe we can develop a nickel oxide nanocrystal that by solution processing. And this whole transport layer has very good surface weighting properties, so that would be beneficial for making larger area devices. So, and to reduce the interface recombination, so we also modified this surface of nickel oxide using a cross-linkable small molecules. We call this VMPB. So in this way, we can also increase the performance of the vital band gap subcells in the tandem devices. And as a result, due to the improvement in the whole transport layer for vital band gap perovskite, and also the additive for the nano band gap perovskite, so we can increase the efficiency up to almost 25% from the previous 22.7%. And also from the EQ inspector, we can see that the current matching condition for these two subcells is quite reasonably good. And we sent one devices also for certification at JET in Japan. And we got a stabilized certified efficiency of 24.2%. And this result has been included into the Professor Martin Green's solar cell efficiency tables last year. And we can also see that from this issue that the single junction perovskite solar cells for the same device area, the efficiency is 21.6. So it means that there's no reason that the tandem devices cannot be fabricated in larger area compared to the single junction devices. And we also even tried to make even larger area devices by making the active area 12 centimeter square on 6 by 6 inch by centimeter substrate, and we can still get efficiency about 21%. And also due to the surface passivation in the narrow band gap subcell, so we can get a higher VOC than previous work, and we increase efficiency to 25.6% at that time. But still, we are thinking how to increase the efficiency beyond even 30%, or at least comparable to the efficiency of perovskite silicon tandems. I think in the previous work, we mainly focused on narrow band gap subcell, so we haven't carried out much work on the wider band gap perovskite material, and the VOC losses in this subcell is still quite high. And also we can see that the current density is not high enough. That is mainly limited by the narrow band gap subcell, and also the parasitic absorption losses in this tunneling recombination. For example, if we can further increase the open circuit voltage and also slightly increase the short circuit current density, I think we will be able to achieve efficiency above 30% in the coming 2 or 3 years, I think. So because we know that JSC is a major limitation in these all perovskite tandem devices compared to crystallized silicon or CIGS tandem devices, because they can already get a JSC approaching 20 milliamp per square, and we can only get a 16 milliamp per centimeter square. I think we have to do more work on light management, especially using more transparent, like the charge transport layer and also the front electrodes. And also we have to manage the surface refraction. I think that is also something neglected in this field. And also we have to further improve the materials quality, especially the mixed lead tin-based nanoband perovskite, so that we can use even thicker absorber layer to get higher photocurrent density. Because we can see that from the EQE of the previous record devices, we see that close to the band gap, the light absorption is still not sufficient due to the limited thickness of 900 nanometers. So from optical simulation, we found that if we can use a thicker absorber layer for this bottom cell, so actually we can increase the photocurrent density in the tandem devices, especially if we can get a thickness above 1.2 microns, we can get even higher current density in the tandem devices. So that is the reason that we also work on this direction. So we improve the materials quality of this nanoband perovskite, and we use its thickness to up to 1.2 microns in the tandem devices. So recently we get this new record performance of 26.4%. That is what we can see, that we can mainly improve the JSC values of the tandem devices. So at the end, I will briefly discuss the stability of the tandem devices, all perovskite tandem devices, because many researchers may suspect that this all perovskite tandem devices is not stable for practical applications, especially considering the tin oxidation. Actually, we found that this may be not a major issue if we can well encapsulate in the devices. And also, we found that these materials of the charge transport material is very critical for device stability. For example, if we can replace the organic BCP with the metal oxide materials, even for unencapsulated devices, we store the devices in air for 500 hours, we can see that the performance degradation is negligible. And also, if we encapsulated the devices and put the devices under the solar simulator and operation for 500 hours, so we can still maintain almost 90% of their initial performance if we can well design the device structure. I think this is also quite a similar phenomenon in the early study of perovskite single junctions. If we are not carefully selected the charge transport materials, we can easily degrade the device performance. And another things we have to think about is the thermal stability of the all perovskite tandem devices. And because all the high efficiency nanoband perovskite solar cells, we have to use organic whole transport layer. We call it P.dot PSS. And from the work of the Michael McGehee, Professor Michael McGee's group, and we found that like this P.dot based whole transport material, they lead to very poor thermal stability, because the interface between the P.dot and the mixed lead tin perovskite is not thermally stable. So even actually from the early year of 2019, so we are also thinking about how to replace this P.dot layer maybe with more thermally stable materials, such as the nickel oxide nanocrystal film. But we can make a good performing solar cells, but the device performance is still not as good as that we obtained in the P.dot based devices. And I think in the future, we still have to do much work on this. And also another thinking point to improve the thermal stability is that we have to remove this BCP in the inverted perovskite devices, and we can do this with metal oxide. And we found that the BCP layer is not thermally stable because they will aggregate after a thermal stretching at 85 degrees. And also by using this metal oxide layer, we get another benefit is that we can prevent the diffusion of the metal electrodes into the perovskite film, as we can see from the XPS spectra. But still, as we showed that previous, we use a 1 nanometer thick gold in the tunnel recombination junction. And we found that if we use the porous nickel oxide nanocrystal film as the whole transport layer for this bottom junction, and we found that the gold will diffused through the nanoporous nickel oxide film and diffuse into the perovskite film. So this will be very bad for the device performance. And to avoid the metal diffusion in the tunnel recombination junctions, and we replace this gold layer and also with a very robust ITO nanocrystalline film. And we can see that using this ITO nanocrystalline as the tunnel recombination layer, so we can still get a very comparable device performance. And the good things that we can significantly increase the thermal stability of the Tandem devices by using the ITO nanocrystalline as the charge recombination layer. And at the end, so we fabricated the Tandem devices only using metal oxide as the charge transport layer, and also we use MA-free perovskite for both subcells. So we found that actually the Tandem devices can have very promising thermal stability. So it can maintain 85% of their initial performance after thermal stressing for 2,500 hours. I think this will pass the IEC standards on this point. And we also found that even under MPP operation, it can still maintain like 80% of their initial performance after 900-hour operation at 65 degrees. So at the end, I will briefly summarize what we have talked in here. So the first is that we have to prevent the tin oxidation in the precursor solution. And what we can do is by adding metallic tin powders or other reducing agents in the precursor solution. And this is very crucial to achieve long diffusion lengths and high efficiency in the solar cells. And we also developed a tunnel recombination junction that is free of the using of sputtered ITO, and this can also give us very high performance Tandem devices. And by using this surface anchoring sweet ionic additive, so we can improve the performance, scalability, and also the stability of the Tandem devices. And at the end, we show that by using the all inorganic-based charge transport layers and methyl ammonia-free perovskite absorber layers, we can get a thermally stable Tandem devices. And at the end, I thank all my group members who work very hard to have the very nice results as I show here. And also I have thanked all the collaborators who helped a lot in the past few years to set up the group and also to carry out research projects together. And I have to thank all the funding agencies, and also thanks for your attention. So if you have any questions, you can also drop me an email for further discussion, I think after this webinar even. So, yeah, thanks.
Okay, thank you, Professor Tan. Okay, it's a very, very nice presentation. So you show the big rapid progress in the all perovskite Tandem devices. And you also show the very excellent results regarding the long-term stability at high temperature. So you already show the Tandem devices satisfy the the 85, the condition is quite nice work, very excellent work. Okay, so in today's agenda, we have the 30 minutes round the table discussion. However, I want to have some short questions from our audience. So as you can see in the chat display, so there are several questions for Professor Bakr. So could you answer some few questions from our audience? So there are seven.
Thank you.
You can choose some comment from the audience.
Yeah. Thank you, Professor. And I very much enjoyed, by the way, Professor Tan's talk. I learned a lot and very exciting results. So thank you for giving me that chance to talk first. So I think the first question is a question about whether why aren't single crystal thin films why are they rarely used in orthotopic perovskite devices? And the answer is simple. Is actually it's growing single crystal perovskite thin films, halide perovskite thin films is actually so far is very difficult. We can make our films thick. So far, you know, on the microns range, but thin films that are single crystal is still a challenge, and I don't know many people who could do that very well. If it can be done very well, it will be a very big step for the field. So maybe I'll answer one more question, then I'll give the floor to Professor Tan. So how do we test the EQE and because the perovskite single crystal, because it's small, we have to use a shadow mask. We have to make sure we're measuring the areas very carefully. You know, it's very important that you measure the area carefully, because you can't rely on just the area of your electrode, because the diffusion length of the carrier is quite large, and it causes an overestimation of your effective current when if you don't measure your area carefully and you don't use masks to cover the area very well outside the device. Professor Tan, would you like to ask a few questions, because I know most of the questions came first because I gave the first talk, but maybe Professor Tan would like to answer a few.
You can continue if you like. I think.
Yeah. I think just we can do this so that the audience would benefit, just in case we run out of time.
Okay. Thank you. So I will read the first question from the audience. So, how to spin P.PSS on the gold? I think because since the weighting is pretty poor, and without the protection of ITO, how to avoid the damage to the P.PSS? I think this is a very critical and important question from the point of view of processing. So as I mentioned in the talk, this 1 nanometer gold, I think it is not a continuous film. It is more like a nanoclusters deposited on top of the metal oxide, the tin oxide. And we found that the weighting of this tin oxide is still quite good, and even after evaporate like 1 nanometer of gold. So the spin coating of P dot on top of tin oxide is not an issue. I think it is quite easy. So I think you can try it, and then you will find it is quite easy. And without the protection of the ITO, how to avoid the damage to the P dot PS layer? I think this is a very critical question. So because if without this ITO, if we directly spin coating the P dot layer on top of the wide banding perovskite, it will dissolve this wide banding perovskite because of it is a water solution of the P dot. So as I mentioned, the critical low is for the atomic layer deposited tin oxide layer. This layer can protect the front wide banding perovskite subcell, so that we can easily do P dot layer spin coating on top of that without any damage. I think this is very critical. And the second question is, do you have any experience or advice on the development of a monolithic battery middle layer? So I'm not quite clear about the question. What is monolithic battery middle layer? Because I haven't worked. I have never worked on the battery, the chemical cells. Sorry for that. So,
Yeah,
maybe the third question: what are the biggest problems encountered in the current development of CIGS and perovskite stack? I think the audience is mentioning the perovskite CIGS tandem devices. I think it is also a very good direction to develop CIGS and perovskite tandem devices, because the band gap of CIGS is around 1.0 electron volt. So it is a very good band gap suitable for tandem devices. I think currently the record efficiency in the community is 24.2%, obtained by the group of Professor Steve Ablett in HZB in Germany. I think the efficiency is not as high as that of perovskite silicon tandem. It is not like a scientifically not possible. It's more like not many groups are working on this direction. I think the biggest problem it could be that the surface of the CIGS layer is a bit rough. So you have to be very careful in design and fabricating the tunnel recombination junction, and how to fabricate the high quality perovskite films on this rough CIGS layer. And for other things, I think there's no problem to get a high efficiency. So maybe Professor Bakr, you can answer more questions.
Yeah. So I'll try to go. Some of the questions are also not so easy to understand, but I think one of the audience is asking, why is single crystal perovskites not as efficient as polycrystalline perovskites? And the answer is probably it's a matter of fewer developments and fewer people working on the area right now. On single crystals, we've only been figured out how to make very good PIN solar cells, and PIN solar cells are not. They have advantages in terms of processing, but they're not as efficient as NIP solar cells, even for polycrystalline devices. So so far, all our single crystal devices have, for practical reasons, because of crystal growth conditions, have been on PIN solar cells. So that's one reason. The other reason is that we still haven't applied many of the passivation methods that people have applied to polycrystalline thin films or have discovered. We haven't yet applied them to single crystal devices. So it's just a matter. I think it's a matter of trying and a matter of just work. Giving more time to the system. It's not that it's either inferior. In fact, just looking at our experience is that we're finding, there aren't that many people working in this on this kind of device. Maybe a few groups, and yet we've achieved already impressive efficiencies. And I think there's a lot more to be done, because there's many configurations that have been done in polycrystalline devices that haven't been even yet explored in single crystal devices. So I think the second question one of the audience members is asking is about 2D perovskites and whether they're some kind of single bullet to solve the stability of perovskite devices, and if we can do machine learning to sort of predict their band gaps, or I'm not sure that I'm the best person to answer this. Probably Professor Sukta is a better person to answer this question, whether 2D perovskites will, how they'll grow or how they're going to emerge. Or, you know, my view is that they've been, you know, the material itself sounds very stable, and it's a very interesting material in terms of composition and versatility. But when people have put it traditionally, what we've noticed is when they're in devices, they're not that much. In fact, they seem to be less stable than 3D perovskites. So we still haven't understood why, you know, as a material, it seems to be more stable, but when you put it in a device, the stability isn't that much better. But maybe Professor Suk or Professor Tan can give a better view on the future of how do they think 2D perovskites are going to impact perovskite solar cells, and whether they will have quasi 2D perovskites, whether they will have a big effect on this field or not. I'll let them maybe briefly give a comment on that.
Okay, thank you for your good answers against the several questions. From now, we would like to have the opportunity to discuss some issues based on your presentation. So let's start with the Professor Tan regarding the narrow bandgap perovskite materials. So you already used the narrow bandgap as the bottom cell and the large bandgap for the top cell. So you use the all perovskite materials to fabricate the tandem devices. So as you know, well, the ideal bandgap to reach the more highest performance would be in the range of the 1.3 to 1.4 electron volt in bandgap. So if you use the mixture of the tin and the leather based materials, the suitable bandgap could be satisfied by using that kind of materials. So do you think? How do you think you can fabricate the very efficient devices with the single junction of with the mixture of the tin and the leather halide perovskite materials? So I think if you push the more performance, higher performance with the narrow bandgap, we can expect the more higher performance with the all perovskite tandem devices. So can we comment? Can you comment how we can achieve the high performance with the single junction of the mixture of the tin leather based the devices?
Yeah. So thanks for your question, Professor Sok. I think that is a very interesting topic. Whether we can fabricate maybe ideal bandgap perovskite single junction devices, so that by using the mixed lead tin based perovskite, so that we should be able to further increase the efficiency of the single junction devices. Only use the lead, because the lead-based perovskite, the lowest bandgap, I think is around 1.5. Yeah.
Yeah, right.
if we can lower it down to 1.34 or 35, I think that is the most ideal band gap for single junction devices. Yes, I think in principle it's possible to tune the band gap by mixing lead and tin to get band gaps values between 1.2 eV and 2.3 eV. I think that is possible. But one challenge is that we found that in this community is that, for example, if we want to make a 1.35 EV for this ideal band gap, so the tin ratio is around 25% to 30%, the tin ratio. And it's very interesting that in this mixed system that if the tin ratio is only 25% or 30%, usually the electronic quality of the perovskite film is very poor. And the reason is still not quite clear.
So
and if the tin ratio is around 50%, then usually we get the best quality for this mixed system.
Yeah.
So could be something. They say that if the tin ratio is low, they say some study they carried out a DFT simulation. They say maybe the two cations they will form a kind of like a separated material in the film. So, and that is one thing. And they also found that some study found that if the tin ratio is low in the material system, usually the defects formation energy is lowered a lot. So it means that the material is tend to form a high trap density, and also the energy levels is shifted to the middle of the band gap. So that means the material forms quite a large number of deep trap sites. That is quite bad for the device performance. So I think we still have to work a lot to understand the materials, especially the mixed lead tin based perovskite materials, especially if we want to shift to the ideal band gap, because this area is not much explored. Maybe we can find some synthetic approach that we can fabricate quite high quality materials.
Yeah. Okay. So if so, Professor Bakr, have you ever tried to grow the single crystalline the mixture of the lead tin halide perovskite materials?
Thank you for this question. So actually, shifting the band gap is a really important thing, and I think one of the reasons we were interested in single crystals because actually the band tail of single crystals, because they're so thick, actually extends a few tens of nanometers further than the polycrystalline films, and I think the FAMA mixture is already just a bit less than 1.5 eV. So we think with we're not that far already, but I think the bigger problem we have with single crystals at the moment, I think, is the interface. The VOC is a bit smaller than we'd like, and I think the reason is that because we grow these crystals from solution, we get some usually. So the interface crystallizes leftover liquid from the solution can damage the interface slightly, and so this is the biggest problem we have, and so we think the biggest room for improvement is getting the VOC to go up. The issue with the tin is that we haven't tried this yet, but and I think it will be an interesting thing to try.
Okay.
We know how to grow pure tin halide perovskite single crystals, and we know how to grow lead, but we haven't yet grown them both together. But what we see is the issue of oxidation. Even though crystal looks nice, the crystal looks beautiful, there's a big issue of oxidation. And I think this is a big area to explore. I don't have an answer for you, but I think people should look at it, and we should be growing this kind of mixture. But I think the bigger priority, at least we see, is that we need to improve the VOC of the single crystal solar cells first, before we, I think that's the biggest place for improvement, obvious improvement for us. I think so.
Okay, thank you.
Thank you.
So let's continue to discuss with the all perovskite tandem devices. So the first time is the quite expert in both silicon and perovskite solar cell. So nowadays, so many companies are focused on the realization of the tandem devices with the silicon and the perovskite materials. So as we shortly discussed with the president before starting our presentation, the HGB in Germany already achieved the 29.8 in the performance, almost close to 30%. So our the dream in solar devices is to achieve the around the 35% in very near future. So some experts believe the silicon perovskite tandem cell will be the good candidate to reach the value. So in terms of the boards, the Perovo and silicon Perovo devices, each one will be more promising in the future. So you just all focused on the all perovskite device tandem devices. So some company mainly focused on the silicon perovskite tandem cell. So each one is more the promising.
Yeah, this is also a very good question from Professor Sok. That is, which technology direction would be more promising for commercialization at the end? I think that is your main point of the question. Yes, I think from the perspective of efficiency, I think both structures, perovskite, tandem, or perovskite crystalline silicon tandem, I think at the end, I believe they will get a very similar efficiency around the 30% or even higher. I think could be maybe practical limit would be around the like 35% or 33%. And beyond that would be very challenging, as we can also see from the tandem devices made by 3-5 semiconductors, because I think this is quite comparable. And for the commercialization point, maybe would be that the commercialization of perovskite silicon tandem will be earlier than perovskite tandem, because the crystalline silicon industry is already very large. Yeah, it has a huge market nowadays. And if we can build a new technology to increase the efficiency of the current silicon solar cells, for example, by adding the perovskite on top, and so that we can increase the efficiency by 5 or even 8%, absolutely. And this will be very interesting for the industry, because this means higher efficiency can reduce the leveraged cost of PV electricity a lot. And this is the reason why so many like crystalline silicon companies are interested in this technology. And I communicated with a lot of people in the industry, and they say that if you guys can solve the stability issues, they will definitely invest millions and millions of dollars in this direction. I think it is also quite similar for perovskite and perovskite tandem devices. If we can finally solve the issue of stability, they will be also willing to invest millions of dollars in this technology, because all perovskite tandem devices can make even cheaper, yeah, PV modules, because the silicon it is still, although it's very cheap, but compared to perovskite materials, the fabrication is still more costing. And also for perovskite tandem devices, maybe we can find some other markets that is crystalline silicon cannot do. For example, the flexible modules, or even some for space applications, because nowadays also the NASA in US, and also I think the European Space and Agency, and they carried out some initial works and demonstrate that like a perovskite material is very tolerant to like the space irradiation. Yeah, so it means in the future maybe we can make a very efficient and flexible and very light multi-junction tandem devices only by using perovskite materials, and we can send out to the satellite or space shuttles in the future. So that is some like a initial market that maybe crystalline silicon cannot do in the future. Yeah.
Okay, thank you. So, Professor Bakr, you can join any discussion with the tandem devices.
Thank you. Yeah, I mean, of course, Stan is the expert, and I think also one of the reasons when Stan mentioned space applications, people are looking for weight to
Okay. Okay, thanks. Yeah. So let's discuss with the single crystalline the perovskite thin layer on substrate. So to fabricate the efficient devices with the single crystalline the perovskite layer, so we have to solve the big issues, the interface between the perovskite and the substrate. So according to your results, you already use the hydrophobic substrate. So if so, if you want to use the inorganic electron transporting material, others, how can we deposit the single crystalline layer on that kind of substrate?
So thank you. This is an excellent question. Right now, actually, our limit. So what we do is we grow the crystal directly on the substrate. Okay, and that's how we ensure that there's a good interface between the HTL and the HTL and the perovskite crystal. But actually, not many substrates allow you to grow nice crystals. Many substrates, if you try to grow crystals, you start seeing very small nuclei forming, and you actually get a polycrystalline film. And you really have to. There's only a few HTLs that we found so far that allow you to grow, nice crystals and not nucleate many small crystals.
I see.
Typically, we found that they've been hydrophobic, but that's not the only important characteristic. And I think right now this is the limitation we have. It's just a matter of practically growing the single crystals. Now, if we find, I think it's important that we find a substrate, a material, an HTL or ETL that's quite smooth, that allows you to also grow these kind of single crystals without nucleating a lot of sites. And that's the challenge. It's not a it's mainly a challenge of crystal growth challenge, I think, that we're facing at the moment. The other challenge that we've noticed is because there's no grain boundaries and the crystal is one big crystal. You know, if you go through any kind of thermal cycling, you have you know, thermal expansion. You know, a lot of strain builds up in the crystal, and you can get sort of detachment with from the interface. But when you're dealing with polycrystalline films that are very thin, and there's a lot of grain boundaries, you know, the strain that builds up at the interfaces, I think, is much less. And so the chances of getting a detachment from the interface between the perovskite and the interface is much smaller than in the case of a single crystal. If you have a thermal strain that builds up, yeah. I think these are the challenges we see in single crystals at the moment.
Okay, thank you. We got a very big lesson from your explanation. So the first time, you can join this discussion. No, nothing. First time. No, nothing.
I actually have a
question. Professor Bakr has explained all the details and quite nice.
Okay.
I have a question for Professor Tan. I mean, maybe it's a naive question. Why we noticed that the wide band gap layer is much thinner than the narrow band gap layer in the tandem cell. Why could you maybe elaborate why is that? Is this an intentional, or you know, is there a design reason for that?
Yeah, this is a very good question, and also very important question actually. There's a main difference in the light absorption coefficient between the lead perovskite and the mixed lead tin perovskite. And the mixed lead tin perovskite, the light absorption coefficient, I think it is much lower than that of lead-based perovskite, especially close to their band gap. Yeah. So it means like we have to use at least 2 micrometers of mixed lead tin based perovskite to absorb the most of the light close to the band gap. But currently we can only get good quality films at the thickness of 1.2 microns. I think in the future we still have to improve the materials quality so that we can increase the diffusion length, and this way we can use even thicker absorb layer for this bottom cell. And for the top wide band gap, because we use is the Fa cesium based perovskite, the light absorption coefficient is quite high. Typically, when we use 400 nanometer thickness, we can already get the matched current density as we want. Yeah.
Okay.
That is the main difference in the light absorption coefficient of these two different materials. Yeah.
Okay. So because the scheduled time is already over, so I would like to close today's the agenda. So big thanks to everyone who has attended this webinar hosted by the Ecomat. So in particular, I would like to express my sincere thanks to two invited speakers, Professor Tan and Professor Bakr. Okay, I hope we will see you soon in some conference and other everywhere. Okay, thank you. Thank you for joining here.
Thank you. Thank you, Professor.
Okay, thank you.
Bye-bye.
Thank you, Stan. Thank you. Take care. Bye-bye.
Good night.
Good night. Yeah.
Good night.